here we have one router with 3 network interfaces, which means there are 3 subnets. So it's quite apparent here, but I think I asked you this question last time, how many subnets are here? And I think there was a little bit of varying answers. Right? Remember I said we took a poll last time. So potentially it could be 3 subnets, 6 subnets, or 9 subnets. So how many subnets are here? So a hint, it's 3, 6, or 9. So how many subnets does this network contain? So let's see a show of hands. I'm going to give you 3 choices. I want everybody to raise their hand to at least one of these choices. So instructions clear? Are there 3 subnets? Okay, a few people saying there are 3. Are there 6 subnets? Okay, a few people saying there's 6. Or are there 9 subnets? Okay, no one says 9. So 9 is not correct, and that's correct. So it's either 3 or 6. Okay? So what was how do we create subnets? Every network interface of every router creates a subnet. So we see 3 routers each with 3 interfaces. Seems to imply that there are 9, right? But notice that in pairs, 2 of the subnets of pairs of routers are connected. So they form the same subnet. So there are actually 6. Okay, so the 6 subnets are the 6 islands in blue shown on the graph here. Okay, I think that the folks who said, I think you said 3, right? Do you want to tell me why you said 3? No, not you, the gentleman behind you. You said 6. Oh, you raised your hand. Somebody said 3. Who said 3? It's okay, I just want to make sure we've cleared it up. Okay, there were a few 3s, but maybe a bit shy now. Yeah? Yeah, they don't have any hosts on them, but in fact, they have 2 network interfaces on them. A host is nothing but a network interface. So, for example, for this subnet here, I think you're asking about subnets like this, right? Actually, there are 2 network interfaces. The network interface from this top router and the network interface from this bottom left router. They are connected together. Yeah, so equivalently, there are actually 2 hosts. They just happen to be the network interfaces of the router. Okay, the consequence of this is if you're at home and you're connected to, you have your cable modem or your optical modem connected to your wireless router. Now, your computers connect to your router, but between your modem and your router, that's a subnet. Yeah. So a host is an endpoint. Yeah, it's either the beginning of the connection or the end of a connection. Everything else in the middle has to do routing. Okay? Does that help? Right, remember we said we have this end-to-end principle. Intelligence exists at the endpoint. So the end hosts are doing, doing that task, the intelligence task. Okay? Okay, so there were 6 here. So again, there are 6 subnets, and the principle is that every network interface of every router defines a subnet. Last time we discussed that IP addresses are 32 bits, right? We represent them by what's called dotted decimal notation. We take these 32 bits, chunk them up into 4 chunks of 8 bits and convert those 8 bits to a decimal, right? So we get something like 137.132.144.155, right? So each of those decimals will be between 0 and 255, right? 8 bits, 2 to the 8, is 256. So we have 256 values from 0 to 255. Now, so we saw before that IP addresses are structured in a hierarchical fashion, right? So nodes that are geographically close to each other have IP addresses that are similar, right? So the similarity, when we looked at the addresses I assigned to the examples that we discussed last time, the similarity had to do with the first few bits of the IP address. And those first few bits I called the subnet part. So the IP address has a subnet part and a host part. And we represent that subnet part in two ways. We can represent it by a number. For example, here I've shown you 200.23.16.0/23. That /23 tells you that 23 bits of the IP address are part of the subnet, right? The remaining 9 bits are part of the host. Okay, that's the first way we represent a subnet, by /23 and the prefix, the 23-bit prefix that that corresponds to the given address. The second way we represent it is through a subnet mask. And a subnet mask is nothing but an IP address where you have all ones in the subnet part and 0 in the host part. Okay, so for example, the subnet equivalent of this is this 255.255.254.0. That's a /23 subnet mask. Okay, often you will see it in both ways. If you go into the TCP/IP settings in Windows, you'll have to enter in the subnet mask. Right? They don't represent it as a number /23. They represent equivalently as an IP address, defined in the subnet mask format I've shown you here. Okay, so this way of representing a subnet, which is, remember, a range of addresses, is called classless interdomain routing. Okay, now I always found this strange that things are called classless. If something is classless, there should be a classful, right? That's why you emphasize classless. So actually, classful networks were how the internet started off initially. Okay, you had class A addresses where the subnet part was a /8. You had class B /16 and class C /24. And that's all you had access to. You only could have a class A, class B, or class C network. But currently we can have any length of subnet we want. Okay, so the general form is you have, yeah? Sure. Yeah, I'm done. So. So I'm not sure why AWS would do that. The current protocol does not limit you. Yeah, I mean, of course, you cannot have a subnet of of size 32, right? Because then there are no hosts, and you can't have a subnet of size 0. Correct? Yeah. So all right. Yeah. Okay. So that's CIDR. Let's see. Okay, so we've been talking about IP address. I think at this point we understand the hierarchical nature, right? Okay. So let's talk a little bit about how we, IP addresses are handed out. So how does a host get an IP address? So when you come to NUS and you connect to the wireless network, how do you get an IP address, right? I mean, you could do it manually. You could assign it manually. It's not clear that the network would, accept that, given sort of security policies and so on. What typically happens is the IP address is assigned to the host automatically, using, by the network, using a protocol called DHCP, Dynamic Host Configuration Protocol. Now, I'm not going to cover DHCP because you could design it if you wanted. If you sat down to figure out, okay, how would I design a protocol to assign IP addresses to hosts that enter the network, I'm sure you could come up with something, right? So the protocol is nothing but a bunch of handshakes. So maybe the only tricky thing is if you come up to a network and you want to get an IP address, who do you know, like how do you know who to ask for the IP address? Like you say, hi, I want an IP address. Well, who do you say hi to? That's maybe the only tricky part here. So any thoughts? How would you request an IP address? Through the router. Which router? The one the one immediately that you're connecting to? But that router may not be configured or authorized to give you an IP address. Right? You would, for security reasons, you might want to centralize this. So how would you do it? Via the? Well, you're in some sense, yeah, so the question is, I'm at the ISP. I'm at Singtel's network, and I want an IP address. What? The gateway, but that's the same thing that Chen Hui said. You may not know, like the gateway may not be authorized to give you an IP address. So let's say you would centralize the control of IP addresses at a central server. Yeah? But you can't ask the gateway, you don't know how to talk to the gateway. Ah, there you go. So say it louder. Yeah, so you will broadcast. Remember, broadcast is when everybody gets the message. So what you're going to do is you're going to come up to the network and you're going to broadcast your request. And when you broadcast your request, it will get to the DHCP server. And the DHCP server is configured to handle your request. Okay, so with that tricky part out of the way, yeah, it's nothing but a bunch of handshakes, right? Okay, so that's why I'm not going to cover the DHCP protocol. There's nothing else tricky in there. Okay, but this is how a host gets an IP address. This is if you're not hard coding it. Somebody came and asked me a question a few weeks ago that they had two computers and they connected them through an Ethernet cable. Who is that? Is that gentleman here? And he didn't know why, like it didn't work. And eventually he ended up hard coding the IP addresses on the two machines, and then they could communicate. Because the addresses were different, they were on different subnets, and two subnets cannot communicate. Right? The routers are not going to be able to handle those packets. So you could hard code it, or you can get it automatically through DHCP. So that's how a host gets it. So how? Okay. Anyway, so I told you I don't want to cover it. So that's how a host gets it. You get it from your ISP through the DHCP server of the ISP. Then the question: how does the ISP get it? Right. So the ISP gets it also from maybe like a super ISP, or eventually it has to go back to an organization called ICANN. But an ISP will get a block of addresses from its authority, and it will then have the right to parcel those addresses out to its customers. So for example, Singtel gets a block of addresses, and for example, NUS is a customer of Singtel. NUS can get a block of addresses. So for example, here's an example of an ISP that has the address range 200.23.16.0/20. So that means this is a /20 subnet, right? That means what? 20 bits for the host part, and how many bits for the, 20 bits for the subnet, and how many bits for the host? The gentleman in the back row, the two of you, hi. So how many bits for the host part? A bit louder? A bit louder? Well, how many bits are in an IP address? A bit louder. You're too far. Okay, so if I have 20 bits for the subnet part, how many bits for the host part? 12. Yeah, not 20, right? So are you good? So 12, right? So if there's 12 bits in the host part, how many hosts can Singtel's address range or this ISP's address range handle? Yeah, 2 to the power 12, correct. And what the ISP is going to do is it can parcel those out. So for example, with its /20 address range, the ISP could take 3 bits of the host part. Remember, there's 12 bits in the host. It takes 3 of those bits, and it uses them to identify or to create a bunch of subnets. This is 3 bits. I can create 8 subnets. And then I'm going to create /23 subnets. So this 20 was the ISP's assigned subnet. It's going to take 3 bits from the host and append it to the subnet and create 8 subnets of 8, you can call it sub-subnets. Okay? And these 8 subnets, it can now sell to different organizations. So for example, here are organizations 0 through 7 that have these 8 subnets. So we saw how you can split a subnet into a bunch of smaller subnets. Okay? If you went the reverse, that's called aggregation. If you're given a bunch of subnets and asked, how do I aggregate, then it's the reverse. Okay? So this is how an ISP gets it. Now remember, the reason that this hierarchical structure, the reason it helps us is it allows a router to advertise prefixes, right? So for example, it is controlling some router is controlling. So for this ISP, it has a /20 address space, right? So and there are 2 to the 12 hosts in its possible hosts in its subnet. Now those hosts could get packets, but the router that's at the edge of that ISP doesn't have to remember all those 2 to the 12th hosts. It just has to remember or advertise the 20-bit prefix and tell the rest of the world anything that's destined for an address that has 20 bits prefix that identifies my subnet, send to me. Right? And so that's what's happening here. So these organizations are, this fly-by-night ISP is the ISP with the /20 address. This is the internet. Anything that has this /20 address space, this ISP says send to me. Okay? Now, it could be that some organization wants better service. So they want to have 2 alternate routes. So this hierarchical structure allows us, like for example, organization 7, is that who I chose? Or organization 1, let's say, wants to get better service. It goes to another ISP, and it also says, okay, I'm going to connect to you, get service from you, and get packets routed through you. So now this ISP can now also just advertise the /23 subnet that corresponds to organization 1. So now packets have the possibility of taking 2 routes to organization 1. Okay, so this hierarchical framework is very flexible. All right, so that's how the ISP got it. And then I said, and eventually you have to trace this back to an organization called ICANN, the Internet Corporation of Assigned Names and Numbers, and ICANN is responsible for managing IP address spaces as well as, for example, friendly names like www.iamthegreatest.com. Right? If you want to get that domain name, you have to go through a registrar who eventually has to go through ICANN. Okay, so ICANN is a very powerful body. It also manages DNS. Okay, so any questions on IP? So that's like sort of concludes the discussion of IP. I want to move on to a few other functions that are implemented at the network layer. Okay, and then after that, so we'll do that for the rest of today. Then on Monday, we'll talk about routing. Okay, we'll talk about routing algorithms. Okay, so that's the plan. All right. Okay, the next thing I want to talk about is a topic called network address translation, or NAT. Now, NAT is going to connect to something that we discussed in transport layer. Do you remember I asked you to remember something in transport layer? Because I talk about it at the network layer? Demultiplexing and multiplexing. Okay? So NAT is like multiplexing and demultiplexing that we discussed at the transport layer, but at the network level. Okay, so remember the demultiplexing and multiplexing was given a computer with a network interface. There's a whole bunch of processes on the computer generating packets. All those packets have to get multiplexed onto the line, onto the single network interface coming out. Then when packets come back, they have to do what? What has to happen to them? Yeah, so processes generate packets. Like I have a tab in Chrome generating packets to be sent out, like a YouTube request. I'm playing YouTube in a tab in Chrome. What has to happen when the packets come back? Because that network interface, is it tied to my Chrome application? What is my interface tied to? To what? The interface identifies what? Yeah, the host. Right? So what has to happen to the packets coming back? Demultiplex, right? So you need another addressing mechanism. What addressing mechanism did we use? To address the process, yeah? Yeah, so do you remember how we address the packet? How we address the process? No, we have to address the process. Like for example, I have a Chrome tab running on a computer. I have my mail client running. I have my Twitter client running. They're all on the same network interface. How do we address them? Yeah, a bit louder. We use port numbers, right? Remember in the transport layer header, there was a port number field. So this is just reviewing multiplexing and demultiplexing. The reason it's connected here is that this is happening at the network layer. So for example, in network address translation, you have a router, a NAT router. So this router here, this is the NAT router. And the NAT router is going to serve as sort of the gateway to the network here that's behind the router. I call it a local network, a home network. It has many names: private network, VPN, firewall. So there are many names for sort of this setup here. But what happens is the packets, as they're leaving the private network, get multiplexed through the NAT router. And when they leave the network, the local network, it's as if they're coming from the NAT router. So they're multiplexed there. Then when packets come back, what has to happen? They have to be demultiplexed. And just like we did at the transport layer, we're going to use port numbers to do the addressing. Okay? So now let's kind of talk about this a little bit more about why we want to do this. Why do you think you might want to do this masquerading process that I mentioned? Yeah? Yeah? Exactly. So Daniel is talking about security, right? So you're saying that if these sort of hosts that are inside your home, let's say, are completely visible to the internet, they're very easy to be hacked into, right? And we're not security experts, right? So we haven't, hardened these machines so that they're not hackable, right? So what this NAT router does is it effectively disconnects your home network from the internet. Does that make sense? It's going to disconnect, which means that you get this security benefit. Can anybody think, what's the second benefit I get? There's a second sort of ancillary benefit. Yeah, louder? You expand your address space because this network is no longer connected to the internet. So if you want to, you could use Google's IP address in your home network, and no one would care. No one would know. Right? I mean, you typically don't, right? Since we've been talking about IP addresses, I'll point out that there are a couple of IP addresses that are reserved for private networks. 10 dot, 192 dot, and 172 dot. All of these are you won't find them on the internet, as a public IP address. They're reserved for private networks. Okay? So these are the two benefits. Now, you got to keep this in mind. I'm disconnecting the network. So you might think, hey, I've disconnected the network. That makes the network useless. But how is it at home I can surf the internet? Right? I can watch my video of cats playing with yarn at home, right? Or I can watch my favorite, I can, run Netflix and watch my favorite movie. But I'm telling you it's disconnected. So let's see how to reconcile that. We're going to do it through an example. The text is there for you to read on your own. I'm going to do it through an example. Okay? So the idea is that the NAT router is going to masquerade, right, as all the hosts in the network. Right? And because it's masquerading, it's going to have to do address translation. And it's going to have to do some housekeeping. And it's going to have to keep a table to account for the changes it made so we can undo those changes. Right? That's the demultiplexing. So let's say I have three hosts here, 10.0.0.1, 2, and 3. And now the NAT router has two network interfaces. So it has a 10.0.0.4 as well as a public IP. The 138 dot is its public IP. The 10 dot is its IP on the private network. Okay? Now here's what the NAT router is going to do. When a packet comes, so let's say that 10.0.0.1 sends a packet to a web server, 128 dot whatever. I know it's a web server because it's port 80. Okay? Port 80, web servers typically run on port 80. All right? So this is fine. So host 10.0.0.1, doesn't know or doesn't care about the net. It just sends a packet. It makes a request to YouTube, for example, to get a video. Now, what the NAT router is going to do is it's going to change. So look at this. The source IP is the host in the first packet sent from the host. The source IP is the host. The destination IP is the web server. When the NAT router gets it and forwards it, look what it did. It changed the source IP to itself. The destination IP remained the same. Do you see the change? This is the translation part of network address translation. All right, and now the port here, the source port was 3345. That's a randomly assigned port assigned by the operating system to, for example, the web browser. So what's this 5001? Who made that up? The NAT router did. Why did it do that? So it could keep track. So notice in its table, it's going to say, on the LAN side, on the local area side, I got a packet from 10.0.0.1, 3345, port 3345. I translated that to my IP address at port 5001. So this is the housekeeping that the router is going to do. Of course, now it's kind of straightforward what's going to happen. The packet will come back from the web server, but it will be destined for the NAT router. This is where you get the security. The internet doesn't see these computers. The hosts inside the NAT are invisible to the internet, right? The NAT router is not. But the idea of having sort of a single point of entry into the network is you can configure the security on this, right? You only have to be responsible for configuring the security on the NAT router. Okay, so the packet comes back here. Now the NAT knows what changes it made, right? It had taken something from port 3345 from host 1 to port 5001. So when it sees a packet coming back for 5001, it can undo the translation. That's the demultiplexing. Okay, so it's going to demultiplex and get it back to the host. So is this clear? Yeah. Yeah. Are you talking about? Yeah. I mean, the sequence is 1, 2, 3, 4. Yeah. I transmit and I receive. Are you talking about this 1, 2, 3 here? Yeah, there's no combining happening here. Yeah, if there's four, so these are arbitrary addresses that are assigned. The 1, 2, 3, 4 are not special, meaning the addresses 10, 0, 1, 2, 3, 4 are not special. They are just assigned either by DHCP or by the network administrator in a manual fashion. There's nothing special there. Okay, does everybody get that? Yeah.
Possible that there are so many outgoing requests from the hosts that eventually the router runs out of.
Okay, so the question is, can we run out of port numbers? Yes. How big is the port field? Remember from transport layer header? 16 bits. Yeah, so you can run out, yes. But you have a lot of ports, right? 2 to the 16, 2 to the 16 ports. Now, many ports are reserved, okay? For example, SSH uses port 22, HTTP, the server uses port 80 and so on. There's a whole bunch of reserved ports, but there's a lot of unreserved ports, especially the large port numbers are, yeah. Of course, you can run out, but it's unlikely. But you can, absolutely. Okay, so do we get the basic idea of NAT? So this means even though I disconnected the network, when I'm behind the NAT, I can still send packets out. Right? This is good. If I'm behind the NAT, I can surf. If I'm behind the NAT, I can make a Skype call. But what happens if the person I'm calling is also behind the NAT? Now we have a problem, right? Because the hosts behind the NAT are supposed to be invisible. So it looks like we didn't really bring full functionality back. I can start a connection from inside the NAT. But I cannot start, like if you're at home and I wanted to WhatsApp you, if you're connected to your home network, and I want to Skype you or do a FaceTime call or WhatsApp call, right now, as of now, I can't do it. So we have to solve this problem. It's called the NAT traversal problem. Right? We have to find a way. Now, if we just allow the NAT to kind of not do its job, then we lose all the security benefits and the address space expansion, right? So we have to solve this NAT traversal problem. So let's get to that. You could do it there's kind of a couple of simple ways. Like since NAT works by doing the address translation and then undoing it, you could, for example, go into your NAT, configure it, like that. This is solution 1. Configure it, and then broadcast it. Tell the world. Go post it on Facebook, right? Or on Twitter and say, hey guys, I'm accessible through 138.76297 port 5001. Then I can contact you. But that's very difficult and inconvenient, right? That's solution 1. Solution 2 is a way to do that kind of more automated. But it's still not ideal. It's still the same kind of clunky solution. This is not what Skype, WhatsApp, WeChat, FaceTime, this is not the solution they use. Does anyone know what solution these other services use to do NAT traversal? No, that's kind of this. Yeah. Yeah. The idea comes from you can start a connection from inside the NAT. Can you build on that? I'm not sure exactly what stun is exactly. What?
You ask you have a middleman.
Yeah.
You send him your public basic.
Yeah. Correct. Yeah.
Then everyone else can see it.
Yeah. Correct. But technical jargon, no. Explain it like that. Okay? Good. So anyone else? So I think you're on the right track. How could you solve this problem if you have the ability to start a network connection from inside your NAT? So I have user 1 and user 2 here, both inside NATs. They want to talk to each other. This guy doesn't know this guy exists. This guy doesn't know this guy exists. Yeah? Local area network. Can you elaborate? Yeah. But how do I know you exist? I don't know you exist. That's the core problem. Because of the NAT or the VPN. I told you, NAT, VPN, firewall, all the same thing. Just a slightly different services, right? Inside that box. So, anyone else? Yeah? Well, if they don't have access to the internet, you're done, right? You still need a connection to the internet. Maybe you have a proxy or something, yeah, but you still need a connection. So the idea is you have a middleman. You have a third party that's in the public internet. And if both parties can contact this party, the third party can make the connection. And that's precisely what is the solution that we use here. Okay? So for example, Skype, there's a Skype relay. Now, since you downloaded the Skype app, the app knows how to contact the Skype server. It's hard-coded into the app. But I think with services like Stun, you don't have to hard-code. Okay? But for these kind of services, there's like security issues. So there's a third-party server. From inside the NAT, you initiate a connection to the third-party server, the service that you want, and the other side does the same thing, and this third-party server makes the connection, shares the information, and then traffic can flow in a peer-to-peer fashion. Okay? This is why you can stalk people in WhatsApp, right? See when they were last seen, and when they were, whether they're online or not. Yeah.
This is the one where you're directly peer-to-peer or you're using the relay.
So the relay is used to make the initial connection.
Okay, so it's directly
Then traffic goes peer-to-peer. Because otherwise it's not scalable. Right? Imagine all video calls having to do this. It's not scalable. But yeah, you're right. So traffic flows in a peer-to-peer fashion after the connection. So the third-party relay exchanges the contact information. All right, so this is how we do NAT traversal in the current internet. Okay, so we're done with NAT. I'll just say a few more things that are implemented at the network layer that are not routing. I want to finish up the small things. So ICMP is a protocol for sending control signals and error messages. Okay, it's used by ping and traceroute. On the first day that I met you, we did ping and traceroute, right? I did some live ping and traceroute. It's using ICMP messages. If you carefully looked at it, you would see some information about ICMP in the responses given to you by the operating system. Okay, but anyway, this is just to show you some of the error and control signals, control messages that are available in ICMP. That's ICMP. I want to say something about IPv6. The current internet uses the internet protocol or IPv4, right? We are in the process of transitioning to v6. What's the benefit of v6? v6 tries to simplify things. Fixed header, no fragmentation. Remember we talked about fragmentation and reassembly in IPv4. v6 does not have that. It tries to simplify things. This is the header, the anatomy of a header of an IPv6 packet. We see that it has some similar things as before. There's a source address and an IP address. Actually, but there's a big difference. Can anybody see the big difference in the source and IP addresses? Like, how big is an IP address and IP in v4? So how big is an IP address in v4? Do you know? Yeah, I heard you. Do you know? 32 bits. So do you see difference? What's the difference? What? A lot bigger. Actually, it's a lot bigger. You know why, right? Because how many IP addresses are there now with 128 bits? Yeah? Say it. 2 to the power 128. It doesn't sound big, but actually it's very big. I converted it to base 10. It's 10 to the 38. And then I was trying to come up with a good example of how to see how big it is, and I found out that it's close to the number of atoms on the surface of the Earth. Right? So you could assign an IP address to every atom on the surface of the Earth. It turns out, unfortunately, not the whole Earth. It's about like 40% of the Earth if I want the whole volume. But if I take the surface, there's about 10 to the 34. So I could give an IP address to every atom on the surface of the Earth and still have, a bunch more left. So it's very big. It's unlikely we're going to run out of IP addresses. The other interesting thing to note here is there's a flow label. You remember when we did transport layer, we talked about rethinking the end-to-end principle, and I told you the key was flow identification. Awesome. IPv6 has a flow identifier built into it. So we don't have to make inferences anymore. The examples I gave you last time, we had to make inferences about if this was from this flow or that flow. Here we have an explicit flow label. The last thing is, so there's a bunch of, anytime there's a protocol change, things will change. You cannot switch every router from v4 to v6 overnight. It's not feasible, right? It's impractical. So we need a way to evolve from v4 to v6. The way we do it is through, we get a graceful evolution through something called tunneling. We essentially add another layer. That's all it is. We add both a v6 and a v4 network layer, and you encapsulate. So you have a bunch of v6 routers like A and B and E and F, and let's say in the network somewhere there's a bunch of v4 routers. Well, you want those v4 routers to be actually almost invisible to the rest of the network. So what you do is you need to have some special functionality built into those edge routers so that they encapsulate the v4 traffic. So for example, they will create like a virtual tunnel. Okay, so the logical view will look like this. It'll just be v6 routers connected, right? But what's really happening underneath is encapsulation. Okay, so you have this sort of v6 traffic being encapsulated into a v4 packet, sent on the v4 network, and then you undo it. This is essentially layering, right? This is precisely what the different layers do. So we just need to have special routers, special v6 routers on the edge that can do this encapsulation. So these special routers can talk both v6 on one end and v4 on one end. All right, and this will allow us to evolve gracefully. Eventually, we will get to v6, but it will take some time. Okay, so that's it. Okay, so any questions? Actually, I was going to do something like, why don't we start this? If you need to go, it's okay. We've been trying these polls, right? Oh, I don't want that. Sorry, that was wrong. Right, so you guys can just go to pollev.com/youcan'tseeme. All right, and just start. When I get a bunch of responses, I'll move to the next one. So go to pollev.com/youcan'tseeme. Okay, and just put in your student number. Okay, I'll give you guys a minute to do that. I just have a couple of questions about aggregation. I want to make sure that you got the idea of network aggregation. Okay, IP address aggregation. Okay, can I get just try to respond quickly, please. So, yeah, if you're having trouble, please raise your hand. I can help you. Okay, I think there's just a few more people. All right, I'm gonna do a countdown. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, excellent. Okay, let's do this one. So suppose I have the IPv4 address range given here. How many addresses are in this range? So some easy stuff, okay? It's okay. Yes, so it's just 2 to the what? So 2 to the what? 2 to the 11, right? Because 32 minus 21 is 11. So this one's okay. What is the first address in this range? Haha, this is not so trivial, right? It might. Oh, I realized I can't. If I think. Let me do a test, okay? I'm gonna just hit go out of full screen. Can you still respond? It's still okay. Okay, good. I'm gonna. You might find this useful. Binary. Hang on. Online binary IP converter. There's a good one, yeah. So like for example, you can convert from IP to binary and binary to IP. So in this thing, it might be useful to take this and actually convert it to binary. Okay? And so now you should be able to figure out what the first address is, right? Because why? We have 21 bits, right? So you take the first 21 bits, which is here, and then you zero out the rest. Right? And then what you actually want to do is convert this from binary to IP. So if you're, it's not that difficult to do, but maybe to save time. So this is the first address in this range. Okay, so what was that? Yeah, so correct, okay? But remember, it's not about the right answer, right? It's about, do I know how to, frame it and get the sort of way forward. All right, so this one I think was pretty straightforward. Now, this is a little bit of a, what's the first usable address in this address range? So that should be easy, right? Because we just can't use the all zeros, right? So the first usable address will be .1. Right, this is why sometimes if I ask you how many addresses are in a range, yes, you can say 2 to the power, right? If I have 11 bits, 2 to the 11 is 2048. But the usable addresses, you can't use all zeros, and you can't use all ones. So actually, I would accept 2 to the 11 minus 2. Okay? Here, so this is pretty okay. How about this one? What is the broadcast address? So again, the 21 bits don't change, but how do you get the broadcast address? You write out the IP address, keep the first 21 bits the same, and do what to the remaining 11 bits? All ones, right? And that's the broadcast address. So you can, actually, I put the number so you can guess. Like, you know it's not 1, you know it's not 4, it's only 2 or 3, and actually you know it's not 2, because that puts all the bits to 1 in the third byte. So I think you can kind of guess. Yeah. Okay, good. Okay, what is a subnet mask? So this is also quite easy. It's 21 bits, right? How do we get the subnet mask? We take the first, what do we do to the first 21 bits? You make them all ones. And what do we do to the last 11 bits? Zero them out. And I think you can also guess which is the correct one, right? Can you guess? Which is the correct answer here? I said you don't need to convert to binary. Yeah. Okay, good. And the last one is, I want you to now aggregate. So in the notes I showed you how to split up. Can you aggregate this? So what is the CIDR aggregation of the following /24 addresses? So there's 4 addresses. Okay. Yeah. So remember, you actually don't need to care about the first 16 bits because they're the same, right? So I mean, just a trick. You don't need to worry about the first 16 bits. Just look at the third chunk of 8 bits and convert it to binary. So this might be a bit tricky, but not really, actually. You think it's 1? Did you say 1? Oh, okay, 2. Actually, you know, for example, it's not /24, right? And you know it's not /23. So you should be able to deduce that. The only question is /21 or 22? Now the /21 uses 3 bits, right? So it creates 8 subnets. But I only want 4. So actually the /21 covers this range. But it covers extra stuff. So the only real answer that's possible is either 2, it's really 1 and 2. And I think, yeah, so you figure it out that what I would think is the right answer here is 2. Yeah. Okay? All right. Okay, so we're done with class. When we come back on Monday, we're going to start talking about routing. And then on Monday and Wednesday, we'll finish up routing. Your homework is due on Thursday. Please come and ask me questions either now or Monday and next Monday and Wednesday. All right, thank you very much.